All right, let's dive right in. We're going to venture into a world that sounds like science fiction, a place where tiny particles can be in a bunch of places all at once, and where reality, well, it seems to change the moment we look at it. Yep, we're talking about the quantum mechanical wave function, and to guide us through its beautiful, kind of bizarre logic, we're going to lean on a classic textbook. Now, right off the bat, if you're thinking, whoa, this sounds complicated, don't worry. You are in excellent company. The legendary physicist Richard Feynman once said that he could safely say that nobody understands quantum mechanics. So let's not think of this as some scary lecture, okay? Instead, think of it as us exploring a thrilling mystery together, one that even the smartest people in history have wrestled with. And our guide on this little adventure, it's the famous textbook Introduction to Quantum Mechanics by Griffiths and Schroeder. We're pulling our ideas straight from this source, so you know we're getting right to the core concepts, the real heart of the theory. Okay, so first up, a revolutionary departure. Before we can really get what quantum mechanics is, we gotta understand how it's completely different from, well, everything that came before it. This is all about appreciating just how big of a break it was from old school physics. And another giant of physics, Niels Bohr, kind of doubled down on that idea. He said, if you're not confused by this stuff, you probably haven't really understood it. So seriously, that feeling of confusion, it's not a bug, it's a feature. It means you're actually starting to get just how wild this new way of thinking is. So, here's the absolute key takeaway. Quantum theory isn't just a minor tweak on the old physics playbook. No way. It's a whole new ballgame. Griffiths calls it an abrupt and revolutionary departure. And that's exactly what it is. It forces us into a radically counterintuitive way of thinking about how the world even works. All right, section 2, from certainty to probability. This is where we really get to the heart of that big departure. We're going to put the old, comfortable, predictable world of classical physics side by side with the strange, new reality of the quantum world. You know, in the classical world, the world of Isaac Newton, everything is kind of like a game of pool. It's totally deterministic. If you have a particle, like this cart here, and you know all the forces on it and where it started, you can predict exactly where it's going to be at any time. We call that x of t. It's a world of pure certainty, no surprises. Well, quantum mechanics comes along and just throws all that certainty right out the window. Seriously, we're not even trying to find a specific position anymore. Instead, we're hunting for something totally different. The particle's wave function. You'll see it written as this cool Greek letter psi. And honestly, this is the main character of our entire story. So, how does this wave function thing actually work? What does it do? Well, it follows its own special set of rules, and those rules are all packed into the famous Schrödinger equation. Don't let the name scare you, just think of it like this. It's the quantum version of Newton's laws. It's the master rulebook that tells the wave function exactly how to change and evolve over time. And this chart just lays it all out side by side. It's so clear. On one side, classical mechanics. You've got a definite position, x of t, and it's all run by Newton's laws. Simple. On the other side, quantum mechanics. The state is the wave function, psi, and it's run by the Schrödinger equation. We've basically swapped out a world of certainty for a world of, probability and indeterminacy. Yeah, and this visual just says it all, doesn't it? On the left, you've got your classical particle, sitting right there at one specific, easy-to-find spot. But on the right, that's the quantum version. It's not a point at all. It's this wavy, spread-out smear of possibilities. It's a totally different way of seeing things. Okay, so you're probably asking, if the wave function doesn't tell us where the particle is, then what on earth is it good for? Great question. The answer is maybe the most important idea in all of quantum mechanics, the statistical interpretation. This is what's known as Born's statistical interpretation, and it's the key that unlocks this whole thing. Here's the deal. The wave function itself isn't the particle. But if you take it and do a little math to it, specifically you square its magnitude, you get something amazing, a probability map. It's a map that tells you exactly where you're most likely to find the particle and where you're least likely to find it, if you decide to go looking. Let's just look at the graph. It makes it super clear. See where the wave is really tall? Up there near point A? That means there's a really high probability of finding the particle right there. And see where it's almost flat, down by point B? Yeah, you'd be super unlikely to find it there. The particle is just existing in a state of potential spread out across all these probabilities. And this is where things get really, really weird. This whole idea of probability leads us straight into a deep philosophical rabbit hole that physicists have been arguing about for 100 years. Let's talk about the measurement mystery. Okay, get ready for the big one. So the wave function is all spread out, right? A wave of possibilities. But when you or I actually go and measure the particle, boom, we find it in one specific spot. Let's call it point C. So the million-dollar question is, where was it the instant before we looked? Well, it turns out there are three main answers, and none of them are simple. First, you've got the realist position. This was Einstein's view. It says the particle was at C the whole time, and our theory is just missing something. Then you have the orthodox position, championed by Niels Bohr. This one says the particle wasn't anywhere specific. The act of us looking at it literally forced it to choose a spot. And finally, there's the agnostic position, which just says, who cares? We can never know, so it's a pointless question. I mean, listen to this quote from Pascual Jordan. It really hammers home just how mind-blowing that orthodox view, the one most physicists actually hold, by the way, really is. Observations not only disturb what is to be measured, they produce it. It's saying that we don't just find reality, we literally create it just by looking. And this picture shows you exactly what they mean by that. They call it wave function collapse. One moment you have this spread out wave of all the possibilities. The next moment, the instant you measure it, bam, the whole wave just collapses into a single sharp spike at the one spot you found it. The reality you see is a direct result of you seeing it. Now, I know what you might be thinking. This all sounds like weird philosophy, not science, but here's the kicker. We have experiments that prove this quantum weirdness is absolutely real. So let's talk about the most famous experiment of them all. Okay, so this is the legendary double-slit experiment. The setup couldn't be simpler. We're going to fire electrons just one by one at a wall that has two little slits in it. And behind that wall, there's a screen that lights up wherever an electron hits. As the first few electrons go through, well, you can see the pattern looks completely random, just a few dots here and there. But just watch. We keep firing them, one after the other, thousands and thousands of them. And slowly, out of that random noise, something incredible starts to take shape. And it's definitely not what you'd expect. If electrons were just tiny little baseballs, you'd expect to see two bright stripes lined up behind the slits, right? But that is not what's happening. And there it is, the final result. After thousands upon thousands of these single electron hits, what do we get? A classic interference pattern, these alternating bright and dark stripes. That is the undeniable signature of a wave. And this leads to a conclusion so bizarre it's hard to even say. Each electron, traveling all by itself, must have acted like a wave, gone through both slits at the same time, and then interfered with its own self. I know, it's mind-bending. So that leaves us right back at the deepest question of all. Experiments like this seem to confirm it. Reality, down at this fundamental level, is just a haze of probabilities, a wave of potential. And it seems to be our act of looking that snaps it into a single concrete outcome. So if the universe only decides what it's going to be when we observe it, then what does it even mean to observe? And that, my friends, is the profound mystery that sits right at the very heart of quantum mechanics.